Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. You are here now, settling into a quiet moment, breathing without effort, letting the world around you soften at the edges. There is nothing you must solve tonight, nothing you must remember, nothing you need to understand all at once, just a slow drift into something vast, something calm, something shaped not by noise or urgency, but by gravity and silence and the gentle structure of the cosmos. Tonight you are going to rest inside the idea of a supermassive black hole, not as a threat, not as a catastrophe, but as one of the universe's quiet giants, a presence so steady and so deeply rooted in gravity that entire galaxies turn around it with the patience of cosmic time. The mind does not need to reach for anything, only to drift, slowly, softly, along the curves of spacetime. Imagine the center of a galaxy, not a single star, not a cluster, but an enormous invisible weight, billions of times the mass of a sun, collected into a region so compact that light itself cannot escape. And yet, from a distance, it is peaceful, unmoving, a constant anchor around which stars flow like a quiet river of points, each star following its orbit with steady precision, each one held in place by a gravity that radiates no light, gives off no gleam, yet shapes everything around it. Supermassive black holes are not loud, they are not flashing, they are not chaotic in the way one might imagine. They simply exist in the deep centers of galaxies, as calm engines of structure, curving space-time in a way that directs the motion of everything nearby. The more massive they are, the gentler their gravity becomes right at their edge. The tidal stretching that would tear an object apart near a small black hole becomes mild and almost negligible around a supermassive one, the difference between a violent gradient and a smooth slope. And so, despite their unimaginable mass, they sit in a quiet state, surrounded by swirling matter, by stars completing slow, deliberate orbits, by gas glowing softly as it warms and cools, and by space that is curved so deeply that it becomes its own silent environment. As you settle deeper into the rhythm of your breath, you can let gravity become a calming idea, not a force that pulls, but a shape that spacetime naturally forms around mass, a curvature that tells matter how to move, and matter, in turn, tells spacetime how to curve. It is a gentle conversation, one that continues without sound, without rush, across millions of light years, every star gliding in the path defined for it, every orbit unfolding with grace. In that central region, in the very heart of the galaxy, the supermassive black hole does not behave like a monster. It behaves like an anchor, a point of stability in a universe that constantly evolves, constantly expands, constantly changes its arrangement of light and matter. When scientists study these immense structures, they do not see them directly, but they infer their presence through motion, the way a star speeds up as it nears the center, the way its path curves sharply in a specific direction, the way light bends as it leaves the region. All of these clues paint an image of an invisible mass, a mass so large that only a black hole could explain it. From far away, and most of the universe is very far away, supermassive black holes are almost serene, so massive that they change the geometry of space, but doing so in a way that feels smooth, continuous, slow. A galaxy turns like a giant wheel around them, hundreds of billions of stars, moving in a dance that takes hundreds of millions of years to complete a single rotation, a cosmic waltz, with the black hole at its center, not as a conductor, but as the silent weight that keeps everything bound. As your mind becomes quieter, you can imagine drifting toward such a structure, not falling in, not crossing the horizon, but simply observing how its presence influences the world around it, how spacetime dips gently near it, how starlight shifts in color as it moves through curved geometry, how time itself changes pace, running more slowly near the immense mass, stretching out, softening, becoming almost syrup-like in its flow. And yet, even as time slows, the black hole does not announce itself, does not shimmer or glow. Its event horizon is dark, perfectly dark, not because it is dangerous, but because the rules of spacetime make it so. The introduction to this idea, to the existence of such enormous objects, is not meant to overwhelm, it is meant to soothe, to remind you that the universe contains structures so stable, so patient, that they have remained in place for billions of years, holding galaxies together, acting as steady focal points in the flow of cosmic evolution. If you could place yourself in orbit around one, in a safe and distant trajectory, you would see stars curving gracefully, each one tracing out a path determined by gravity, each one moving with a calm confidence, as if following a script written by geometry itself. You might see a disk of gas, thin and luminous, circling the event horizon, heating as it spirals inward, glowing in X-rays and ultraviolet light, a soft halo of energy marking the boundary between the visible and the invisible. But even this glow, even this radiation is not chaotic. It is the result of matter becoming part of a deeper gravitational well, a final arc in its cosmic journey, a gentle fall through curved space, guided by the undeniable logic of physics. When astronomers describe these disks, they speak of them with precision, but there is also a kind of awe, because such simple laws produce such elegant behavior, rings of matter flowing like liquid light, moving faster and faster as they contract, until they reach a speed so great, and a region so small that their motion becomes almost timeless. You do not need to understand every detail tonight. You only need to drift with the idea, to let the concepts unfold the way starlight unfolds, slowly, softly, across the universe. There is a quiet strength in supermassive black holes, a sense of structure and permanence, that contrasts beautifully with the delicate motion of stars, the shimmering of gas, and the slow expansion of space. Wherever there is a large galaxy, there is almost always a black hole at its heart, not as a destroyer, but as a foundation, a gravitational center that shapes the galaxy's identity, its rotation, its density, its evolution. As you drift deeper into rest, you can imagine that you are floating in a calm region of space, far from noise, far from any disturbance, with nothing but the soft glow of distant stars around you, and the gentle curve of spacetime guiding your thoughts. This is the environment of supermassive black holes, quiet, still, anchored, profoundly stable, resting at the center of everything, yet invisible, letting the universe arrange itself around them. Tonight, let your mind drift as the stars drift. Let gravity become a calm presence. Let the immensity of a supermassive black hole become something soothing, something steady, something that simply exists, patiently in the dark, holding a galaxy in place. And as the thoughts become softer and the breath becomes slower, you can begin to move gently into the nature of these objects, into the way mass curves space-time, into the idea of a gravitational well so deep and so wide that its influence stretches across an entire galaxy. A place where light bends, where time slows, where matter flows in smooth spirals, and where silence becomes a fundamental part of reality. The introduction settles you here, in a state of quiet curiosity, ready to drift deeper into the science, into the geometry, into the calm mystery of the universe's largest gravitational anchors. And now, as gently as a star completing its orbit, you drift into the next idea, into the nature of a supermassive black hole itself. Mass has a way of shaping the universe that feels both simple and mysterious, a presence that alters the flow of space and time, not through force in the everyday sense, but through curvature, through geometry, through the subtle bending of the fabric that everything moves within. To understand a supermassive black hole, you begin with this idea, that space-time is not an empty stage, but a flexible medium, capable of stretching, compressing, and bending in response to mass. A small amount of mass produces a gentle dimple, a modest curvature, the kind that governs the orbit of a planet around its star, a quiet, predictable motion. But an enormous amount of mass, collected into a single compact region, creates a curvature so deep that ordinary paths collapse inward, so steep that every trajectory tends toward the center, building a gravitational well unlike any other structure in the cosmos. This is the environment of a supermassive black hole. Not a violent scene of swirling destruction, but a smooth, continuous shape carved into spacetime, a well so profound that light itself follows curved routes around it, sometimes bending into loops, sometimes slipping past, sometimes never returning. The word supermassive might sound dramatic, but the reality is quiet, a calm form of extremity, a structure defined not by noise or chaos, but by the pure geometry of general relativity. A supermassive black hole is not a scaled-up version of a smaller one. Its behavior changes with size. Its structure becomes gentler at the edge. Its tidal forces weaken near the horizon. Because the curvature spreads over a larger region, the gradients soften, the shape becomes broader and smoother. This difference is one of the most striking features of extremely massive black holes. The paradox that more mass can mean a gentler experience at the boundary. A smoother descent into the well, a gravitational environment where free fall feels calm, even as spacetime bends to an extraordinary degree. If an object were to approach the horizon of a stellar mass black hole, very close to the surface, the difference in gravitational pull from head to foot would be enormous, stretching the body rapidly, pulling stronger on what is nearer, weaker on what is farther, creating intense tidal forces. But the same motion near a supermassive black hole, with a horizon that stretches across vast distances, would feel almost uniform. The gradient barely noticeable, the forces gentle, even though the total mass is many millions of times greater. This is the counterintuitive essence of supermassive objects, that size transforms severity into softness, that scale reshapes the experience of gravity, that the horizon becomes a wide, smooth doorway, rather than a narrow region of intense change. And yet, despite this gentleness, the underlying structure remains extreme. The curvature near the center remains profound. The interior geometry remains unlike anything else in the universe. But the story of a supermassive black hole is not only about the horizon, it is also about the region around it, the place where matter gathers, where accretion disks form, where light and heat emerge from processes that occur just beyond the point of no return. Matter rarely falls inward in a straight line, not in a universe where everything carries some angular momentum. Instead, it spirals, forming a disk of gas, thin, rapidly rotating, glowing in multiple wavelengths as it heats and compresses. This disk is one of the few visible traces of the black hole's presence, a luminous halo orbiting darkness, revealing temperature through its color, revealing velocity through the broadening of spectral lines, revealing geometry through the way light is bent by gravity. The gas in the disk moves at tremendous speeds, approaching the speed of light near the inner region, its flow controlled by viscosity, by friction between adjacent layers, by magnetic fields that thread through the plasma, by the deep gravitational pull that shapes its orbit. But for a supermassive black hole, the heating process is more gradual than in smaller ones. The inner regions are spread over larger distances. The gradients are smoother. The luminosity is sustained and steady, creating a glow that can persist for long periods of cosmic time. This glowing material provides scientists with clues. It allows them to measure the mass of the black hole, to estimate its spin, to identify the orientation of the disk, to study how matter moves in intense gravitational fields. One of the most important insights comes from observing stars near the center of a galaxy. Their orbits trace the invisible presence of the black hole, moving rapidly when they are closest, slowing as they drift away, following Keplerian paths modified by relativity. Paths that reveal how deep the gravitational well must be, how compact the mass must remain. In the center of our own galaxy, scientists have tracked stars completing full orbits, moving swiftly around a point that emits no light, a point so small compared to the mass it contains that there is no explanation other than a supermassive black hole. These stars act like test particles, tiny indicators of the curvature around them. Their acceleration reveals the depth of the well. Their trajectories reveal the structure of space-time. Their periodic returns reveal the density and compactness of the central object. Through these measurements, scientists infer the mass with remarkable precision. Millions of solar masses confined within a region smaller than the orbit of planets, a gravitational anchor that has shaped the center of the galaxy for billions of years. The presence of a supermassive black hole is therefore not a mystery in the sense of uncertainty. It is a mystery in the sense of awe, an object that cannot be seen directly, yet defines the motion of everything around it, a silent structure that sculpts the inner architecture of the galaxy. The event horizon itself, the boundary that separates the visible universe from what lies beyond, is defined not by matter, not by energy, but by geometry. The place where outward paths cease to exist, where light, no matter how fast it moves, cannot find an outward direction. There is no surface, no wall, no material boundary, only a region in spacetime where the geometry becomes too steep for escape. An observer crossing this boundary would feel nothing special, no change in pressure, no shift in temperature, no sudden impact, only the continuous motion of free fall, as smooth as any motion in a vacuum, guided by the curvature beneath them. The simplicity of this idea is part of its beauty. The realization that the most dramatic boundary in the cosmos is also one of the gentlest to cross, a silent threshold that marks the limits of visibility, but not the limits of motion. The influence of a supermassive black hole extends well beyond this boundary, not by pulling but by shaping, by defining the curvature through which stars and gas must move, by providing a stable gravitational center that guides the long-term evolution of the galaxy. Its presence stabilizes orbits, structures gas flows, and regulates the rate at which matter accumulates in the inner region, sometimes feeding on infalling gas, sometimes remaining quiet for long stretches of cosmic time. In the darkness near its boundary, light curves, time slows, and matter follows paths shaped by principles discovered through mathematics, principles that reveal the deep structure of spacetime, principles that show how gravity is not a force, but a condition, a shape, a curvature. This, at its heart, is the nature of a supermassive black hole, an anchor of geometry, a region where spacetime bends into its most extreme form, a structure that is both simple and profound, silent yet influential, calm yet absolute in its control of nearby motion. And as these ideas settle into your awareness, you drift deeper, ready to explore the next layer, the way these objects shape the architecture of entire galaxies, the quiet gravity that organizes hundreds of billions of stars, all circling a center defined by darkness, and by the gentle curvature of spacetime. When you look more closely at the curvature around a supermassive black hole, you begin to see that gravity is not a force pulling inward, but a slope that objects naturally follow, a consequence of how spacetime arranges itself around extraordinary mass. The depth of this slope determines how quickly objects move when they fall inward, and how strongly light bends as it tries to pass by. But the shape of the slope, the way it changes with distance, is what distinguishes a supermassive black hole from a smaller one. For smaller black holes, the curvature near the horizon becomes steep in a very narrow region, a sudden drop in the geometry, a rapid increase in gravitational gradient that creates intense tidal forces. But for supermassive black holes, the curvature begins gradually, declining slowly over a vast distance, so that the event horizon becomes wide and gentle, a threshold that marks the end of outward paths, yet feels almost soft to anything crossing it. This smoothness is essential to their character, because it means that the region near the horizon does not contain the violent stretching that smaller black holes impose. Instead, objects experience a calm descent, a continuation of free fall, guided by geometry rather than force. The stability created by such extreme mass also influences the space just outside the horizon, where the accretion disk orbits, where gas moves in nearly circular paths, where particles experience a balance between gravity and angular momentum, creating a thin, luminous ring of material that encircles the dark center. This disk is not uniform. Its temperature increases as you move inward. Its density changes with distance. Its speed approaches the speed of light in the inner regions, creating a gradient of brightness that scientists study to infer the properties of the black hole. The inner edge of the disk marks the region where stable orbits end, where no circular path is possible, only inward spiraling motion, a direct consequence of how spacetime curves in the deepest part of the well. This edge is determined by the spin of the black hole, a property that shapes the geometry itself, altering the position of the last stable orbit, changing the efficiency of accretion, controlling how much energy can be extracted from infalling matter. A rapidly spinning black hole pulls spacetime around with it, a phenomenon known as frame dragging, where the fabric of the universe is twisted by rotation, causing matter, light, and even time itself to swirl in the direction of the spin. This effect becomes strongest near the horizon, where the twisting reaches its peak, where space is dragged so rapidly that nothing can remain stationary. Even light must rotate with the black hole, following the spinning geometry. This rotation influences the entire disk, determining how energy is released, how jets form, and how magnetic fields interact with the swirling plasma. The jets themselves, narrow streams of particles launched at nearly the speed of light, emerge from the poles of the black hole, not from the interior, but from the complex interplay of magnetic fields and rotation near the horizon. These jets can extend across thousands of light years, carrying energy far beyond the immediate environment, shaping the evolution of the galaxy, regulating star formation, and redistributing gas on enormous scales. Despite their size and intensity, their formation remains governed by physics that is deeply analytical. The movement of plasma in magnetic fields, the extraction of rotational energy, the geometry of spacetime near a spinning horizon, all of these processes emerge from the same fundamental ingredients: mass, rotation, charge, curvature, and the interaction of matter with the shaped environment around it. Yet even with this complexity, the overall system remains smooth, predictable, almost serene when viewed from a distance, with gas flowing in steady spirals, with stars tracing out calm orbits, with the black hole resting at the center of everything, silent and invisible, yet absolutely shaping its surroundings. This is one of the most striking aspects of supermassive black holes, the way they influence enormous regions without ever revealing themselves directly, the way they act as gravitational anchors. Holding the cores of galaxies in long-term stability, stars near the center move swiftly, their orbits tight, sometimes completing a circuit in only a few decades, their paths curving sharply as they approach periapsis, where speed peaks, where gravity is strongest, where the unseen mass reveals itself through motion. These stellar orbits provide scientists with precise measurements of the black hole's mass, because the faster a star moves, the deeper the well it must be falling through, and by tracking these motions over time, astronomers calculate the exact value of the mass that lies at the center. This method is one of the clearest demonstrations of how supermassive black holes are detected, not through light, but through gravity, not through visibility, but through influence. Even the shape of starlight changes as it travels near such extreme curvature. Time dilation shifts its frequency. Gravitational lensing redirects its path, causing stars to appear displaced, or stretched, or brighter than they should be. These distortions are not imperfections. They are signatures of curved spacetime. They are the fingerprints of gravity operating at its most profound level, offering clues that scientists use to reconstruct the invisible geometry. In a sense, the black hole is never truly seen. Only the effects of its presence are visible. The motion of stars, the bending of light, the glow of hot gas, all forming an indirect portrait, a picture assembled from the behavior of the universe around it. This indirect nature is part of what makes supermassive black holes so intriguing. They are known not through sight, but through cause and effect, their existence revealed by the motion of objects, by the alignment of orbits, by the structure of light around them. And as the understanding deepens, you start to see how these quiet giants maintain their shape for unfathomable lengths of time, thousands of millions of years, remaining at the center of their galaxies, watching as stars form, as clusters drift, as gas flows inward and outward, as the galaxy rotates in its immense and silent dance. A supermassive black hole is neither creator nor destroyer. It is a result of gravity sculpting itself to its own limits, a structure formed by the accumulation of mass, by the collapse of material, by mergers with other black holes, by the steady inflow of gas across cosmic epochs. Yet through all of this, its fundamental nature remains unchanged. A region where spacetime curves completely around itself, a place defined by geometry, anchored by mass, invisible yet luminous through the activity it inspires around it. When you think of what it means for mass to curve spacetime, you realize that the bending is not metaphorical. It is literal. It is the deepest description of gravity that modern physics offers. a framework that replaces force with shape, motion with geodesics, change with curvature, and in this curvature, the supermassive black hole becomes the ultimate expression of gravity's influence, the deepest well, the most complete form of bending, the point where geometry folds into itself with infinite smoothness. As the ideas settle, you drift in thought, following the natural flow of this conceptual landscape, feeling the calmness of the geometry, the stillness of the horizon, the inevitability of inward paths. And slowly, gently, you move toward the next ideas, the understanding that these vast structures do not exist in isolation, that they anchor entire galaxies, that the shape of a galaxy itself reflects the presence of the mass at its center. The story of supermassive black holes now expands outward, from the deep curvature near the horizon to the structure of the galaxy that surrounds them, all bound by gravity, all flowing in the quiet architecture shaped by mass. And as your mind drifts, you step naturally into the next section, the exploration of how galaxies organize themselves around these invisible giants, how their stars orbit like rivers of light, how the entire structure feels the presence of the mass at the center. Galaxies are not scattered collections of stars drifting without order. They are structures shaped by gravity, sculpted across unimaginable spans of time, their forms emerging from the quiet interplay between mass, motion, and the curvature of spacetime. At the heart of these structures, in the deep central regions where starlight grows dense, a single presence often defines the entire shape, a supermassive black hole, silent, invisible, yet profoundly influential. To imagine how a galaxy forms around such a center, you can begin by picturing a vast cloud of gas, slowly rotating, slowly cooling, slowly collapsing under its own gravity, its particles drifting inward, its density increasing as it contracts, its rotation tightening like a spinning dancer pulling their arms toward their core. As this cloud collapses, most of its mass spreads across a wide disk, thousands of light years across, filled with regions where stars begin to form. Their light pushing back the darkness, their gravity shaping the motion of nearby gas. But in the very center, in the innermost region, the collapse can grow more extreme, the density rising far beyond the surrounding environment, until a black hole forms, or until an older black hole from past generations of stars captures the material drifting inward. Once this black hole reaches supermassive scales, its gravitational influence extends far, reaching across light years, establishing the curvature that guides the orbits of countless stars, imprinting its presence onto the structure of the galaxy itself. This influence is not a pull, not a command, but a shaping of space-time, a quiet rewriting of the geometry in which stars move, a subtle bending that determines how each orbit unfolds. Stars in the outer regions of the galaxy do not need to know that a black hole lies at the center. They simply follow the curvature created by the combined mass of billions of stars, and the deeper curvature created by the supermassive object in the core. Their motion is smooth, slow in the far regions, faster toward the center, tracing elegant paths that reveal the gravitational landscape, paths that follow the distribution of mass like rivers follow the shape of valleys. Closer in, the influence of the central black hole becomes stronger, not violently, but steadily. Its gravitational well adding depth to the core, having a measurable effect on the speed and geometry of stellar orbits. In the inner parsec of a galaxy, the stars move with astonishing velocity, their trajectories curving around a point that emits no light, yet controls the entire region, a point where space-time dips into its deepest form. These stars are often young, formed from gas compressed by earlier activity near the center, and their orbits can be highly eccentric. Elongated paths that take them close to the black hole before swinging far outward again. Each orbit becomes a probe of the central mass, each return revealing subtle shifts, each acceleration marking the depth of the gravitational well. And even farther out, the presence of the black hole resonates through the entire galactic structure, influencing the distribution of stars, the density of gas, the likelihood of star formation in different regions. It is as though the galaxy feels the presence of its central mass, adapting its shape accordingly, settling into a dynamic equilibrium that can last for billions of years. The movement of stars in the inner regions creates a kind of cosmic tide, a circulation around the center that reflects the geometry of space-time, with each star adding its contribution to the gravitational field, and the black hole anchoring the overall pattern, holding the deep central curve that sets the tone for the entire system. If you could watch a galaxy from above, from a vantage point identical to no human perspective, you would see its stars drifting like luminous particles in a vast whirlpool, their orbits overlapping, their paths weaving together into a grand, slow spiral. At the very center, you would see a region of heightened motion, a cluster of stars moving in tight curves, their speeds far higher than the stars in the outer arms, all of them responding to the dense mass at the core, all of them living in the deep gravitational valley carved by the black hole. And if you could slow time, if you could stretch millions of years into a moment, you would watch the galaxy's disk rotate gently, its stars gliding around the center like dust motes in a soft eddy, each one following a path shaped by the distribution of mass, each one tracing a story told by gravity. The black hole at the center is not the only defining feature, but it is the deepest source of curvature, the place where spacetime folds most profoundly. The anchor that keeps the galaxy's heart structured, stable, coherent. In many galaxies, including our own, the central black hole is quiet, barely accreting material, letting the surrounding region remain calm and dark, allowing stars to orbit steadily for long stretches of cosmic time. In other galaxies, the central region becomes active, accreting large amounts of gas, glowing in bright radiation, launching jets that extend far beyond the disk, creating a luminous core known as a quasar, one of the brightest phenomena in the universe. But whether active or quiet, steady or luminous, the black hole remains the gravitational anchor, the central mass that gives the galaxy its balance, its orientation, its long-term structure. Even the correlation between the mass of the black hole and the mass of the galactic bulge, a relationship observed across countless galaxies, reveals that the black hole and the galaxy evolved together, influencing each other across cosmic time, growing in tandem, coordinating their development through the flow of gas and stars. This connection is not simple cause and effect, but a deeper interplay between gravity, gas dynamics, star formation, and the redistribution of angular momentum, all of which tie the central black hole to the shape and history of the galaxy. You can imagine the galaxy as a vast, rotating sea of stars, and the black hole as the point where the depth becomes greatest, the place where the gravitational ocean sinks into its deepest trench, a silent basin that defines the movement of the water around it, even if most of the surface never feels the direct pull. The curvature of spacetime near the core affects the overall rotation curve of the galaxy, influencing how stars move even at great distances, subtly shaping the velocity field across the disk, creating patterns in the distribution of gas and dust, patterns that reveal the galaxy's history of mergers, collisions, and internal dynamics. Gravity sculpts the galaxy the way wind sculpts dunes, gradually, persistently, following the logic of physics rather than intention, creating a structure that is both intricate and stable, both dynamic and enduring. The presence of a supermassive black hole contributes to this sculpting, adding depth to the gravitational configuration, helping the inner region maintain cohesion, allowing orbits to remain bound even as the galaxy experiences disturbances. Collisions with smaller galaxies, flows of intergalactic gas, and the long-term evolution of its own star-forming regions. In this way, the black hole becomes a stabilizing influence, not in the sense of control, but in the sense of anchoring the gravitational potential, giving the galaxy a center, a reference point, a deep well into which everything else fits. The galaxy feels this presence, not consciously, but structurally, its rotation shaped, its inner architecture guided, its long-term evolution intertwined with the mass at its heart. And as you let these ideas drift through your mind, you can sense the quiet beauty of this arrangement, a structure thousands of light years across, held together by a point that emits no light, a silent giant that shapes the lives of hundreds of billions of stars. The calmness of this arrangement echoes through the galaxy, from the bright inner bulge to the faint outer halo, to the distant stars tracing their long, slow arcs, all of them responding to the same gravitational story, the same curved geometry, the same central mass. This is the quiet architecture of galaxies, a structure that emerges naturally from the laws of physics, from the interplay between mass and curvature, between starlight and darkness, between orbit and stillness. And as these thoughts settle into place, you drift deeper into the exploration. Ready to move toward the next ideas, the nature of the event horizon itself, the region where outward paths disappear, and where geometry reaches its most profound expression. Galaxies breathe through motion, their stars circulating in vast spirals, their gas drifting in waves, their dark matter forming invisible scaffolding beneath the luminous arcs, and through it all, the quiet gravitational presence of the central black hole continues to shape the inner structure. Never loudly, never forcefully, but with the steady influence of curved spacetime. When you imagine a galaxy, it is easy to picture the spiral arms, glowing with clusters of young stars, wrapped loosely around the core like gentle swirls of paint. But the heart of the galaxy, the region near the central mass, contains an entirely different environment, dense, dynamic, and deeply influenced by the invisible well at its center. Stars near this core do not move in slow, wide arcs. Their orbits tighten, their paths bend sharply, their speeds rise dramatically, as though gravity itself grows more focused, more precise, more concentrated. This concentration is not a force pulling harder. It is space-time becoming more curved, more steeply shaped, creating a deeper gravitational valley that stars naturally follow, like water flowing through a canyon carved by ancient tides. These central stars often travel in elongated loops, their closest approach bringing them very near the black hole, where their speed peaks, where their trajectories reveal the mass at the center with mathematical clarity, and then they swing outward again, slowing as the gravitational influence weakens with distance. Through these cycles, astronomers measure the mass of the black hole, because only an extremely compact and massive object could cause such rapid motion. Only a supermassive black hole could confine millions of solar masses within such a small region. Only that structure could carve space-time so deeply in the galactic center. But the story does not end with the stars. The gas in the galaxy also responds to this central presence, drifting inward under the combined influence of gravity, cooling, colliding, accreting, falling slowly toward the center where the curvature deepens. Sometimes this gas forms a rotating ring, sometimes it settles into a disk, sometimes it becomes turbulent, depending on the past history of the galaxy, its mergers, its flows, its interactions with other large structures. When the inflow becomes dense enough, the central region can brighten dramatically, forming what astronomers call an active galactic nucleus, a core so radiant that it outshines the rest of the galaxy combined, powered entirely by the slow spiral of matter into the gravitational well, by the conversion of gravitational potential energy into light, by the friction and compression of gas in the accretion disk. And yet even in these luminous moments, the black hole itself emits no light, its darkness unchanged, its horizon silent, its presence known only through the glow of the matter around it, and the jets that are launched from its poles when magnetic fields twist and reconnect near the spinning core. These jets are among the most astonishing features in astrophysics. Thin beams of plasma accelerated to nearly light speed, extending across thousands of light years, cutting straight through the intergalactic medium, carrying energy far away from the center, sculpting the gas in their path, sometimes regulating the formation of stars by heating the surrounding environment. Even though these jets are powerful, their formation is governed by orderly processes, by the rotation of the black hole, by the structure of magnetic fields, by the motion of charged particles, by the physics of plasma, and by the geometry of spacetime near the horizon. This combination of gravity and magnetism creates a feedback loop, a quiet but persistent mechanism that influences the galaxy on large scales, preventing some regions from forming stars too quickly, allowing others to gather dense clusters and shaping the long-term structure of the galaxy. In this sense, the central black hole becomes part of a galactic ecosystem, not acting in isolation, but participating in the flow of gas and stellar evolution, balancing the tendency of gas to collapse with the tendency of radiation to heat and disperse it, a dynamic equilibrium that lasts for billions of years. The relationship between the mass of the central black hole and the mass of the galactic bulge is one of the clearest indications of this interconnectedness. an empirical pattern showing that galaxies with larger bulges almost always contain larger black holes, and that the growth of the galaxy and the growth of the black hole follow parallel histories, suggesting that they evolved together, influencing one another through the quiet exchange of mass and energy. This correlation is not superficial. It is a sign that the central gravitational well plays a long-term role in shaping the inner architecture of the galaxy, helping regulate how stars form in the central regions, how gas flows inward, how the bulge grows over time. Imagine drifting above such a galaxy, seeing the luminous arms extending outward, the faint halo surrounding the disk, the bright, dense bulge at the center, and deep within that bulge, a point of absolute darkness, shaping the curvature that holds the whole structure together. The stars in the bulge move in all directions, not in orderly spirals like those in the disk, but in randomized orbits, creating a spherical swarm, each star feeling the pull of the collective mass and the deeper pull of the black hole near the center. This mixture of motions creates a dynamic environment, a region where gas and stars interact, where collisions are more likely, where star formation can proceed in bursts, where the central black hole receives a steady supply of material, not in a continuous stream, but in waves and cycles shaped by the evolving bulge. The entire bulge becomes a living record of gravitational history, a fossil of past star formation, a repository of older stars, a structure reflecting the balance between collapse and pressure, between rotation and randomness, between the energies released by the central activity and the cooling of gas over cosmic time. And all the while, the black hole sits at the center, not controlling, but guiding, not pulling, but shaping the geometry through which motion unfolds. It is the deepest valley in the gravitational landscape, the place where spacetime bends most profoundly, the point toward which stars accelerate when they come near, and the point around which the entire galaxy finds its symmetry. When you consider that most large galaxies contain such a structure, and that the mass of these black holes can reach billions of solar masses, you begin to see how essential they are, how they represent not an anomaly, but a fundamental component of galactic architecture. Galaxies are not galaxies without their centers. They are not stable unless something anchors the core, something provides depth to the gravitational potential, something carves space-time into a shape that millions of stars can occupy without flying away or collapsing inward too quickly. The black hole does not act alone in this shaping. The mass of stars in the bulge also contributes. The dark matter halo also provides structure. But the black hole creates the deepest part of the well, the final curve that defines the inner region, the place where space-time reaches its most extreme geometry within the galaxy. This deep curvature is what allows stars to orbit stably, what allows gas to settle into disks, what allows the bulge to maintain its shape, what allows the galaxy to withstand perturbations from encounters with other galaxies, absorbing collisions, reshaping itself, yet always retaining a coherent center around which new structure can form. The quiet giant in the core does not speak, does not shine, does not send out signals beyond the occasional burst of radiation from accreting matter, yet its presence is written everywhere in the motions of the stars, in the shape of the bulge, in the distribution of gas, in the very way the galaxy exists. And as you picture this whole structure, you sense the calmness of it. The way gravity creates order on the largest scales, the way curvature gives form to the dance of stars, the way the black hole becomes the silent heart of the galaxy, shaping everything around it through the simple, patient geometry of spacetime. As these thoughts drift through your awareness, you move naturally toward the next layer, toward the horizon itself, toward the boundary where light can no longer escape, toward the quiet region where geometry reaches its most extreme expression, a gentle transition, as the mind glides from the scale of galactic structure to the intimate shape of the event horizon. The event horizon is often imagined as a kind of wall, a boundary in space where reality itself becomes dangerous or unstable. But in truth, its nature is far more subtle, far more elegant, and far more deeply rooted in the geometry of spacetime. It is not a surface, not a barrier, not something that interacts physically with matter or light. It is simply the place where every path, every direction that an object could move, leads inward rather than outward. To understand this, you can imagine spacetime as a landscape, a vast terrain that slopes downward toward the black hole, where the paths of motion become steeper and steeper as one approaches the center, until finally, right at the horizon, the slope becomes so deep, so perfectly angled inward, that no trajectory can climb back out. A particle at this boundary does not feel a shock, does not sense a change, does not experience an impact. It simply continues moving according to the geometry beneath it, following the natural flow of the curved spacetime. From its own point of view, nothing special has occurred. The laws of physics continue normally, forces behave the same way, the speed of motion is unchanged, the passage of time feels continuous. This smoothness is one of the most striking properties of the horizon. It is a region defined entirely by perspective, by how an observer outside the black hole sees the flow of time, and by how space-time itself determines the possible paths. From the outside, objects approaching the horizon seem to slow down, their clocks appear to tick more slowly, their signals become redshifted, their motion becomes more and more drawn out, stretched across time from the perspective of a distant observer. This stretching can be so extreme that the object never appears to cross the horizon at all. Its image lingers, its light becomes fainter, its wavelength lengthens until it fades into invisibility. But this fading is an artifact of perspective, a difference between the time experienced near the horizon and the time experienced far away. For the falling object itself, the moment of crossing comes and goes without disruption. Time flows smoothly, motion continues peacefully, and the curvature of space-time becomes the only guide to its path. This is one of the most profound lessons of general relativity, that gravity is not a force tugging on objects, but a shape that space-time takes, a curvature that defines the natural paths, and that the horizon is merely the place where those paths point inward, with no outward direction available. The idea of a Schwarzschild radius, the distance from the center at which the horizon forms, is simply the point where escape velocity equals the speed of light. Not because something physical blocks the motion, but because the geometry no longer provides any path that leads outward. This radius grows with mass, and for supermassive black holes, it becomes immense, spanning distances larger than entire planetary systems, a region where the curvature deepens steadily, without sharp edges, without abrupt changes. And because the radius is so large, the gradient near the horizon becomes shallow, creating an environment where tidal forces are weak, where the difference in gravity from head to foot is minimal, where objects can drift through without being stretched or torn. This gentle boundary contrasts with the extreme intensity of smaller black holes, where tidal forces become overwhelming near the horizon, creating violent gradients and making the descent into the well far more hazardous. But here, near a supermassive horizon, the experience is serene, a calm continuation of free fall, a smooth extension of motion through curved space, a transition marked not by force, but by geometry. Light approaching the horizon behaves differently from matter. Its path bends, sometimes looping around the black hole, sometimes being captured, sometimes escaping after circling multiple times. These looping paths form the photon sphere, a delicate region where light can orbit the black hole in nearly circular trajectories, not because it wants to orbit, but because space-time curves so completely that the straightest possible path becomes circular. This sphere is unstable, a precarious balance, where the smallest disturbance sends light inward or outward, a region that contributes to the ring-like structure seen in images of black holes captured by radio interferometry, a glowing outline formed by light that spends extra time in the curved region before escaping. Time behaves differently near the horizon as well, slowing relative to distant observers, stretching into long, gentle intervals. As the gravitational potential deepens and the curvature becomes more extreme. This slowing is not felt locally. The falling object experiences its own time normally, but to a distant frame. The object's clock appears delayed, its rhythm softened, its pulses lengthened, as though time itself becomes diluted near the boundary. The horizon marks the division between regions where outward travel is possible and regions where it is not. But the interior remains governed by the same physical laws, the same geometry, the same continuous structure. What changes is the shape of time's direction. the tipping of light cones toward the center, the rearrangement of causal paths, so that all futures lead inward, all motions converge, all trajectories point toward the singularity. This singularity is not a place in space, but a place in time, a point in the future of anything that crosses the horizon. A destination dictated by the geometry, not by choice or by force, but by the inherent curvature of spacetime itself. The singularity remains hidden, shielded by the horizon, never visible, never exposed to the rest of the universe, not because it is physically defended, but because the boundary prevents any signal from escaping outward. This invisibility is one of the defining features of the black hole. The way it protects the deepest curvature from ever being observed directly, allowing only the outer structure to reveal its presence, through light bent in arcs, through gas heated in spirals, through stars moving in tight orbits. Yet even though the singularity cannot be seen, its existence shapes the geometry all the way out to the horizon. Its mass determines how space-time curves. Its presence defines the entire interior region, a region where the alignment of space and time becomes extreme. When scientists study event horizons, they are not studying a surface, but a boundary in the map of possible motions, a threshold where outward directions vanish, a dividing line between what can communicate with the universe and what becomes part of the hidden interior. The clarity of this concept is one of the triumphs of relativity, a realization that gravity is not mysterious force, but predictable geometry, that the event horizon is not fiction, but a mathematical boundary, that the behavior of space and time near such a region can be calculated, measured, observed indirectly, tested through the motion of matter and light. And these ideas do not exist only in theory. They have been confirmed through observation, through the images of glowing rings around nearby galaxies, through the orbits of stars near the center of our own galaxy, through the measurement of light bending, through the redshifting of radiation, through the behavior of gas spiraling inward. All of these phenomena reveal the same truth, that the event horizon is real, that it behaves exactly as predicted, that the geometry near the boundary matches the equations, that the universe follows the logic of relativity with remarkable fidelity. When you imagine approaching such a horizon, you picture the stars behind you becoming distorted, their light bending into arcs, their images stretching into rings, all of them arranged by the curvature of space, a gravitational lens that reveals the depth of the well long before you reach its boundary. You imagine time elongating, moments passing more slowly compared to the outside universe, your heartbeat stretching into a soft echo, your motion feeling calm and steady, even as space-time folds around you. And when you cross the boundary, nothing interrupts the motion, no force announces the transition, no surface marks the place, only the geometry continues, guiding you inward toward the future that all paths now lead to, a future defined by the deep interior curvature, a future hidden from the outer universe. This is the quiet truth of the event horizon. Not violent, not chaotic, not dramatic, but profoundly geometric, a place where outward directions disappear, where the deepest rules of gravity reveal themselves, where space-time expresses its most extreme form. And as you let these ideas unfold, you drift naturally to the next understanding, the processes that occur just beyond the horizon, where matter spirals inward, where energy is released, where jets form, where black holes illuminate the universe despite their darkness. A transition as gentle as gravity itself, carrying you forward to the next part of the story. The horizon of a black hole is often imagined as a violent threshold, a boundary where matter is torn apart, where space-time fractures, where the familiar rules of physics collapse under their own weight, yet the reality is far quieter, far more elegant, and expressed through the smooth continuity of geometry rather than the chaos of force. What lies just outside the horizon is a region shaped by extreme curvature, but this curvature changes gradually. Its gradient softening for supermassive black holes, allowing objects to drift inward without disruption, without stretching, without any sudden change in physical sensation. It is in this region that the behavior of light becomes especially revealing, because light always traces the straightest possible paths through space-time, paths determined entirely by geometry, not by choice, not by force, but by the shape of the gravitational field. As the curvature deepens, These straight paths bend more strongly, causing light to arc around the central mass, sometimes looping nearly all the way around before escaping, sometimes circling multiple times, sometimes falling inward forever. This bending of light creates the optical illusions seen near black holes, the distortions that reveal their presence, the stretched arcs, the luminous rings, the warped reflections of the distant universe. To imagine these distortions, picture a distant star whose light passes near the horizon of a supermassive black hole. The path of that light bends sharply, its image smeared into a curve, its position shifted, as though the starlight is being pulled across the sky by an invisible hand. But nothing is pulling. Nothing is forcing the light into unnatural motion. The path is simply the natural geodesic of curved spacetime, the straightest line available in a deeply warped geometry. This is gravitational lensing, a phenomenon predicted by relativity and confirmed countless times, a demonstration that gravity acts not by tugging on objects, but by shaping the very space in which they move. Near the horizon, this lensing becomes extreme, creating a region where light can orbit the black hole in a precarious balance, a place where the curvature is just right to guide photons along circular paths, a fragile ring known as the photon sphere. This ring is not stable. A tiny disturbance sends the light outward or inward, but the possibility of circular orbits reveals the precision of relativistic geometry, the way spacetime curves smoothly, delicately, yet dramatically enough to allow even massless particles to trace bound paths. This region lies just outside the horizon, a kind of luminous scaffold that frames the silhouette of the black hole, creating the glowing ring captured by radio interferometry in giant observatories scattered across the Earth. The shadow at the center reflecting the absence of escaping light, the ring reflecting the prolonged journey of photons skimming the edge of the curved region. Beneath this ring, inside the horizon, light loses the ability to reverse direction, its future pointing inward, its path guided toward the center by the tipping of spacetime itself. This tipping is often described using light cones, geometric representations of the possible directions a particle can move through space and time. As the horizon draws near, these cones lean inward, their outward opening narrowing, their inward opening widening, until at the horizon, all future paths tilt completely inward, leaving no direction that leads outward into the rest of the universe. This is the essence of the horizon. A rearrangement of the structure of space-time, a shift in what is possible for any object or any signal, not a wall, not a membrane, but a boundary in the map of potential trajectories. Inside this boundary, time itself changes character, not in the sense of flowing differently to the falling object, but in the sense of how its direction aligns with space. The radial coordinate becomes a temporal one, the inward direction becoming as inevitable as the forward flow of time outside, a transformation encoded in the metric of the spacetime, and not in any physical mechanism or force. This is why no object can halt its motion inward after crossing the horizon, why no outward thrust can rescue it, why no trajectory leads back to the universe it came from. The geometry simply does not permit such a path. To the object itself, this inevitability feels natural. It does not experience resistance, does not feel as though it is being forced inward. It simply follows the curvature of space-time. The same way any freely falling object follows a geodesic, its experience unchanged, its local physics intact, its motion continuous. To a distant observer, however, the object appears to slow, its signals stretching into longer wavelengths, their energy decreasing, their frequency dropping, their arrival delayed more and more, as though time near the horizon is becoming diluted, more rarefied, thinning into long, drawn-out moments. This slowing is a direct result of gravitational redshift, a phenomenon where light climbing out of a deep gravitational well loses energy, lengthening its wavelength, softening its frequency, becoming progressively more difficult to detect. In the limit, the signal fades into wavelengths too long to be measured, and the object seems to freeze just outside the horizon. Its image suspended, its clock slowed to nearly nothing, its presence reduced to a faint whisper of radiation. But this frozen image is not the object's true fate. It is simply the way different gravitational potentials distort the comparison of clocks, a contrast between the time experienced near the horizon and the time experienced far away. For the object falling inward, the journey continues smoothly. The horizon passes without fanfare. The interior becomes its new future, and spacetime guides it steadily toward the singularity, a place not defined by location in space, but by the inevitable focus of all inward trajectories. Inside the horizon, spacetime becomes even more distorted, curvature increasing, distances shrinking, and the inward direction becoming compressed into a finite interval, a future endpoint that all paths lead to, a point where the geometry itself ends, not as a physical object, but as a place where classical relativity reaches its limit. This singularity is hidden from the outside universe, protected by the horizon, its secrets sealed behind a boundary no information can cross, its nature unknown, its structure unobservable, its true description requiring a theory of quantum gravity that does not yet exist. It is here that the deepest puzzles of black hole physics arise, questions about the fate of information, about the behavior of quantum fields near the horizon, about the interplay between relativity and quantum mechanics, about the ultimate structure of spacetime when curvature becomes infinite. And yet, despite these unknowns, the behavior of the horizon itself, the way it shapes motion, the way it bends light, the way it governs the possible paths, is remarkably well understood, predictable, testable, and confirmed through observation. When astronomers measure the shadow of a black hole, or track the orbits of stars near the center of our galaxy, or detect gravitational waves from merging black holes, they are indirectly studying the geometry near the horizon, the predictions of relativity, the structure of spacetime in its most extreme form. Each observation matches the equations, each measurement aligns with the theory, each test reinforces the same picture, that the horizon is real, that it behaves exactly as predicted, that the universe follows the logic of relativity with astonishing precision. As you imagine drifting towards such a horizon, you sense the calmness of the journey, the smooth continuation of motion, the quiet deepening of curvature, the way light bends into gentle arcs, the way time stretches subtly, the way the universe appears distorted yet serene. And as these ideas settle into place, you drift toward the next region of understanding. The structures that surround the horizon when matter falls inward, the disks of glowing gas, the fields that shape jets, the quiet catastrophes that illuminate the invisible. A gentle shift, a soft continuation, as the story moves from the boundary itself to the turbulent processes just outside it, ready to enter the next section with the same calm scientific clarity. Matter falling toward a supermassive black hole does not simply plunge inward. It drifts, circles, collides, heats, and forms structures that reveal the invisible gravity shaping its path. Structures that illuminate the dark core of galaxies. Structures that demonstrate how energy can arise from slow, steady infall. The gas approaching a black hole rarely falls straight downward. It carries angular momentum, a residual rotation left over from the larger motions of the galaxy, from the drift of interstellar clouds, from the merging of objects, from the turbulent history of galactic evolution. This angular momentum prevents the gas from collapsing directly into the center. Instead, it spreads out, forming a thin, rotating disk, a structure both simple and extraordinarily complex, governed by hydrodynamics, radiation, magnetic fields, and the deep curvature of spacetime. This disk is one of the most luminous regions in the universe, its brightness arising not from the black hole itself, but from friction, compression, and the conversion of gravitational energy into heat, a process that intensifies as the gas spirals inward, losing angular momentum, gaining temperature, releasing photons at higher and higher energies. The spiral toward the horizon is not fast. It is slow and methodical, a gradual inward drift that can last for long stretches of time, with each orbit bringing the gas closer to the center, each collision redistributing momentum, each compression heating the plasma. As the gas moves inward, its temperature rises to extraordinary levels, so hot that atoms lose their electrons, becoming a plasma of charged particles, responding to magnetic fields, interacting with radiation, creating turbulence and patterns of flow that ripple across the disk. These temperatures produce light in extreme wavelengths, X-rays, gamma rays, energies far beyond visible light, radiation that escapes from the outer parts of the disk, revealing the presence of the black hole to distant observers, marking its position in the cosmos with a soft but relentless glow. This glow is not uniform. It flickers, brightens, dims, responding to changes in the flow of gas, the formation of eddies and waves within the disk, the motion of hot clumps drifting inward, the occasional disruption caused by infalling clouds of material. These fluctuations carry information, signatures of the physics occurring near the horizon, patterns in the timing and energy of the radiation that reflect the curvature of spacetime, and the structure of the innermost stable orbits. The inner region of the disk ends abruptly, not because the gas encounters a physical surface, but because stable orbits cease to exist close to the black hole. The curvature becomes too steep, the paths too unstable, and the gas no longer finds circular trajectories that balance gravitational pull with rotational motion. When the gas reaches this region, its motion becomes dominated by inward free fall, its speed rising as it crosses the last orbit, its energy increasing as it plunges toward the horizon, transitioning from a stable spiral to a descending flow. This boundary, the innermost orbit that remains stable, is a purely geometric feature, a direct result of the equations governing curved spacetime, showing how relativity defines the structure of motion near the horizon, how gravity influences not only the direction of movement, but the very possibility of stable orbits. The disk extends outward for vast distances, its outer regions cool enough to allow molecules to exist, its inner regions hot enough to produce some of the brightest emissions in the universe, a single structure that spans enormous ranges of temperature and density, each part reflecting a different layer of physical processes. Yet even within this complexity, the disk maintains coherence, its rotation steady, its spiral shape persistent, its overall structure guided by the simple fact that angular momentum must be conserved, that the gas must shed its rotation to fall inward, and that this shedding produces heat and radiation. The friction within the disk is not like friction between solids. It is turbulence, magnetic interactions, collisions between charged particles, instabilities that transfer momentum outward, allowing the inner regions to spiral slowly toward the center, while the outer regions absorb and disperse this angular momentum. These interactions create a regulated flow, a gentle but persistent inward drift, a slow release of gravitational energy, a process that can last for millions of years, feeding the black hole at a controlled pace, setting the luminosity of the nucleus, and determining the level of activity within the galaxy. When the inflow of gas is high, the black hole enters a phase of intense activity. Its disk brightening, its corona radiating X-rays, its jets becoming powerful, its influence extending far beyond the central region, regulating star formation by heating the surrounding gas. These jets emerge from the polar regions, narrow beams of plasma accelerated to nearly the speed of light, guided by magnetic fields twisted by the rotating accretion disk, their energy drawn from the rotation of the disk and the spin of the black hole itself. The process that creates these jets is subtle, involving the coupling between magnetic fields and spacetime, the twisting and reconnection of field lines, the focusing of charged particles into narrow channels, the conversion of rotational energy into outward motion. This conversion is one of the most efficient mechanisms in astrophysics, capable of launching jets that pierce through the interstellar medium, carving cavities in the hot gas surrounding the galaxy, heating the environment and influencing the rate at which new stars can form. If the gas around the galaxy cools too quickly, stars form in large bursts, consuming the available material, but the presence of a jet can slow this cooling, injecting heat into the galactic halo, creating a balance between cooling and heating, a feedback loop that stabilizes the long-term evolution of the galaxy. This regulation is one reason that galaxies and their central black holes grow together. Their histories intertwined, their masses correlated, their evolution shaped by the quiet exchange of energy across enormous distances. Even when the black hole is not actively accreting large amounts of gas, its influence persists. The jets may fade, the disk may cool, the luminosity may drop, but the gravitational structure remains, the curvature stays deep, and the memory of past activity is written into the distribution of stars and gas. In galaxies where the central black hole has been active in the past, astronomers often find bubbles of hot gas, expanding cavities, filaments shaped by past jets, echoes of earlier eras when the nucleus was bright, when the flow of matter into the horizon was vigorous, when the energy released near the center reshaped the galaxy. Yet even in its most intense phases, the processes near a black hole remain orderly, governed by physics rather than chaos. Following the predictable equations of magnetohydrodynamics shaped by geometry, guided by the conservation of energy and momentum, there is a tranquility within the intensity, a calm logic beneath the turbulence, a steady rhythm within the spiraling plasma, a rhythm defined by orbital motion, by the conversion of gravitational energy into heat, by the slow drift of matter toward the center. If you could float above the disk, seeing it not with human eyes, but with perfect sensitivity to energy and motion, you would witness an ocean of light, waves of radiation rising from the inner regions, eddies of plasma drifting outward, filaments tracing magnetic fields, bright ripples marking regions of compression, and in the center, a darkness deeper than anything else, a place where no light emerges, a calm void surrounded by the luminous storms of infalling matter. This contrast between luminosity and darkness, between the brilliant disk and the silent horizon, is one of the defining features of accretion, a demonstration that the most energetic regions in the universe are powered by objects that emit no light of their own. That brightness arises from the approach to darkness, that luminosity is born from the journey toward the horizon. The closer the gas comes to the boundary, the more energy it releases, the higher the frequency of the light, the more tightly the plasma spirals, until finally the gas crosses the horizon, its light ceasing, its motion becoming part of the hidden interior, its energy contributing to the mass of the black hole. Nothing announces this transition, nothing marks the moment. The glow simply ends, the path becomes inward, the geometry continues, and the disk adjusts as more gas flows from the outer regions, replacing what was lost, maintaining the spiral, maintaining the luminosity, maintaining the quiet rhythm of infall. As these ideas drift gently in the mind, you ease into the next part of the story, the way supermassive black holes regulate galaxies, the cycles of activity and calm, the feedback loops that shape cosmic structure, the quiet influence that extends far beyond the horizon, a natural continuation, soft, steady, guided by the gentle logic of gravity and radiation. The region surrounding a supermassive black hole is a place where vast energies emerge from simple physical principles, where slow spirals of gas release enough heat to illuminate an entire galaxy, where magnetic fields thread through plasma like fine wires through liquid light, where rotation and curvature combine to create structures that stretch thousands of light years into space. To imagine this region, you picture a disk that is both delicate and intense, thin and turbulent, quiet in its geometry but powerful in its radiation, a structure that forms naturally whenever matter with rotation drifts inward, inevitable, predictable, yet astonishing in its consequences. The disk itself is not solid, not a rigid surface, but a fluid, a continuous sea of ionized gas, each particle moving along a curved path, its motion determined by conservation of momentum, its energy shaped by collisions, its trajectory guided by the curvature of spacetime. As gas spirals inward, the conversion of gravitational potential energy into heat becomes extreme. The deeper it falls, the more energy is liberated, and this increase in energy causes the plasma to glow more brightly, to radiate at shorter wavelengths, to produce the X-rays that reveal the presence of black holes across the cosmos. At the same time, magnetic fields thread through the plasma, born from the motion of charged particles, amplified by rotation, stretched and twisted like elastic strands, their lines looping through the disk, connecting inner regions to outer ones, linking plasma across immense distances. These magnetic fields are not uniform. They vary in strength and direction. They form regions of tension and release. They generate instabilities that stir the disk into turbulence, a turbulence that redistributes angular momentum, allowing the inner gas to move inward and the outer gas to absorb this excess rotation. This process is quiet in appearance, but powerful in its effect, a kind of internal weather system, storms of plasma swirling through the disk, filaments rising and falling, eddies forming and dissolving, each motion contributing to the slow, persistent drift toward the black hole. As the gas moves through these regions of turbulence, its temperature rises further, its density changes, its radiation intensifies, and the inner part of the disk forms a corona, a hot, tenuous atmosphere of charged particles hovering above the disk like a glowing veil. This corona emits high-energy photons, creating a diffuse halo of X-rays, a luminous cloud that floats above the spiraling plasma, a region shaped by magnetic reconnection events, by the twisting and snapping of field lines, by the occasional release of stored magnetic energy into the surrounding space. These bursts of energy are not random. They follow the structure of the disk. They reflect the dynamics near the horizon. They carry information about the geometry of spacetime, encoded in the timing and spectral shape of the radiation. The accretion disk is not alone in the central region, for above and below it, in the polar directions, supermassive black holes often produce jets, narrow beams of plasma that travel at nearly the speed of light. Guided by magnetic fields and the rotational energy of the disk and the black hole, these jets emerge from regions close to the horizon, but not from the black hole itself. Their origin lies in the twisting of magnetic fields within the disk and the extraction of energy from the spinning geometry of spacetime, a process that requires the black hole to be rotating, for only then can spacetime itself contribute angular momentum to the jet. A rotating black hole drags spacetime with it, a phenomenon known as frame dragging, where the very fabric of space twists around the black hole's spin axis, creating a region where nothing can remain stationary, where rotation is woven into the geometry, subtle, smooth, but powerful enough to influence the motion of matter and light. When magnetic field lines thread through this rotating region, they twist, wind up like springs, and launch charged particles outward along the spin axis, accelerating them to relativistic speeds, forming the narrow beams that pierce through the disk and extend far into intergalactic space. These jets can stretch across thousands of light years, carrying energy far from the center, shaping the gas between galaxies, carving long channels of heated plasma through the cosmic environment, and influencing the evolution of galaxy clusters. Even though their origin is smaller than the orbit of planets, at their core, the jets are highly collimated, maintained by magnetic fields that wrap around them, fields that act like invisible walls, keeping the jet focused, preventing it from widening, allowing it to carry energy enormous distances without dissipating. When these jets strike intergalactic gas, they inflate vast bubbles, cavities in the hot medium surrounding galaxies, regions where the density drops and the temperature rises, evidence of past activity, fossil remnants of earlier phases when the black hole accreted more material and released more energy. These bubbles persist for millions of years, their shapes revealing the orientation of past jets, their size indicating the power of earlier outbursts, their edges marking the boundaries between heated gas and the cooler medium beyond. By studying these structures, astronomers can reconstruct the history of a galaxy's central engine, tracing cycles of activity and calm, inferring how often the black hole received fresh material, how quickly it accreted gas, how much energy it released into the surrounding environment. This interaction between the black hole and the galaxy is a feedback loop, one of the quiet regulating mechanisms that keeps galaxies stable over cosmic time. The jets heat the surrounding gas, slowing its cooling, preventing excessive star formation, limiting the supply of new gas that can flow inward, thereby reducing the accretion rate and bringing the system into a form of equilibrium. When the gas eventually cools again, star formation resumes. Some of the leftover gas flows inward, the accretion rate increases, the black hole brightens, jets reappear, and the cycle continues. This self-regulating behavior is one of the reasons large galaxies evolve slowly, why they tend to settle into stable configurations, why their central black holes do not overgrow, why their star formation does not proceed unchecked. The presence of the black hole brings a kind of balance, a quiet governance over the flow of gas, a damping of extremes, a long-term moderating influence. This influence is subtle, emerging not from direct interaction, but from the interplay of gravity, radiation, and fluid dynamics, from the way energy is transported across vast distances, from the way magnetic fields carry information and force through the plasma, from the way the central engine breathes through cycles of brightness and calm. Even the smallest changes near the horizon can propagate outward through the disk, amplifying as they travel, creating waves of brightness, ringing through the radiation emitted by the disk. a reminder that the central region is intimately connected to the larger galactic environment, that processes occurring in regions the size of planetary systems can influence structures larger than entire solar neighborhoods. The black hole itself remains silent throughout this process, its horizon unchanged, its geometry steady, but the matter around it speaks through light, through motion, through turbulence, through the steady glow of the disk and the powerful beams of the jets. As you imagine this environment, you see a balance of energies, a dance of plasma guided by invisible lines, a steady transformation of gravitational potential into light, a flow of matter inward, a flow of energy outward, a harmony between infall and radiation, between darkness and illumination, and at the center, a region where nothing escapes. The deep gravitational well that powers it all, not through forceful action, but through the geometry of spacetime, through the simple fact that matter falling inward releases energy, and that this energy must emerge in some form: radiation, heat, jets, waves of influence reaching across the galaxy. The processes near the horizon do not exist in isolation. They connect to the larger structure of the galaxy, to the rate at which stars form, to the way gas cools and flows, to the distribution of mass, to the long-term evolution of the system. And this connection brings you gently to the next idea: the fact that none of these structures remain static. The black hole grows, the galaxy evolves, their histories intertwine through mergers, collisions, and the slow drift of cosmic time, a natural continuation, a soft transition, into the next section, where the growth of supermassive black holes reveals itself through quiet mergers, through the joining of galaxies, through the gentle rhythm of gravitational waves. A supermassive black hole cannot be seen directly. It emits no light, reflects no radiation, reveals no surface. Yet astronomers have learned to observe it with remarkable precision, not by looking at the black hole itself, but by studying the subtle traces it leaves on the world around it. These traces are gentle, not dramatic: small deflections in the orbits of stars, soft distortions in the paths of photons, patterns in the glow of heated plasma, shifts in the frequencies of radiation, all of them forming a tapestry of evidence, threads woven through space, hinting at the presence of something dense and compact at the center. One of the clearest clues comes from the motion of stars, the way they circle the galactic center, the way they accelerate as they approach an invisible point, the way their orbits close and return after long periods of time. Each star becomes an instrument, a witness to the gravitational field, its motion revealing the curvature of spacetime, its speed announcing the depth of the gravitational well, its trajectory cutting through the inner region like a probe sent by nature. Astronomers track these motions with great care, recording the position of each star over many years, measuring subtle changes, tiny accelerations, the faint wobble of an orbit distorted by relativity, until the mass of the central object can be inferred with astonishing precision. This method has been used to measure the black hole at the center of our own galaxy, a compact region where stars move with extreme speeds, where the mass of millions of suns is confined within a space smaller than the orbit of a single planet, a region where no other known object could exist, no cluster of stars, no cloud of dark matter, no exotic configuration of collapsed remnants. Only a supermassive black hole could create such a gravitational field, only a point of space-time curvature that deep, that compact, that stable. These orbital measurements form a foundation for black hole astrophysics, a direct demonstration that the central mass is real, that its influence is gravitational, that its location is fixed, that its size is too small to be anything other than a black hole. But stars alone do not reveal the entire story. Light also tells a tale. Light bent around the central mass, light stretched by gravity, light warped into arcs and rings as it passes near the horizon. When photons travel through curved spacetime, their paths no longer resemble straight lines. They follow the geometry, bending smoothly around the black hole, sometimes looping in near-circular orbits before escaping, sometimes being captured and spiraling inward. This bending creates a halo of distorted images, a gravitational lens that magnifies and shifts the appearance of distant stars, a lens whose shape is determined by the curvature of spacetime, a signature that can be measured and compared to the predictions of relativity. When astronomers see this pattern, They confirm that the central mass bends light exactly as a black hole should, that the geometry matches the equations, that the distortions occur at the right angles, the right intensities, the right distances. These distortions form part of what eventually becomes the shadow of the black hole, not the black hole itself, but the silhouette created by the absence of escaping light. A dark region surrounded by a bright ring, a ring formed by photons that orbit near the horizon before reaching distant observers. This ring is faint, its structure subtle, its light coming from gas spiraling inward, from photons dragged by curvature, from plasma compressed and heated near the inner edge of the disk. Yet even faint signals can be amplified through technique, through cooperation, through the linking of observatories across continents. This is the idea behind the Global Telescope Array, a network of radio dishes scattered around Earth, all observing the same black hole at the same moment, each dish recording signals with extreme timing precision, down to intervals smaller than the flicker of an atom. When these signals are combined, a virtual telescope the size of Earth emerges, a telescope capable of resolving details finer than any individual instrument could capture. A technique known as interferometry, where the interference patterns between signals reveal the shape of the light source, where the faint glow around the horizon becomes visible, a blurry outline, a ring of fire surrounding a silent void. This ring is the confirmation, a match between theory and observation, a pattern predicted by relativity long before it was seen, a structure formed by the most extreme bending of light, a direct image of spacetime curvature itself. The ring appears soft, its boundaries diffuse, not because the black hole is indistinct, but because the radiation near the horizon is turbulent, the plasma chaotic, the path lengths of photons varied and curved, the resolution limited by the wavelength of radio waves, and the enormous distance between Earth and the black hole. Yet even in its softness, the ring carries precise information. The size of the shadow reveals the mass, the symmetry reveals the spin, the thickness reveals the distribution of plasma. The asymmetry reveals motion within the accretion flow. Each pixel in the image is the culmination of years of observation, months of signal correlation, weeks of data cleaning, all to reveal a region smaller than a plume of smoke on the surface of the moon. A region shaped by gravity so intense that time itself slows to a whisper. But the image is only one part of the observational story. There are also the signals carried by radiation emitted throughout the disk. Soft X-rays escaping from the outer regions, hard X-rays from the corona above the disk, gamma rays from magnetic reconnection events, all carrying information about the structure and dynamics of plasma near the horizon. These signals fluctuate in time, sometimes subtly, sometimes dramatically, the timing of these fluctuations carrying clues about the inner regions, about the turbulence in the disk, about the orbital periods near the innermost stable trajectories, about the interplay between the disk and the corona. Some of these fluctuations are quasi-periodic, gentle oscillations in brightness, soft pulses that repeat over time, tracing the frequencies of motion near the boundary of stable orbits, revealing how relativity shapes the inner structure, how gravity influences the flow of plasma, how matter behaves in curved spacetime. These timing features act like seismology for the accretion disk, vibrations in the luminous surface that reveal the geometry beneath, patterns that encode information about mass and spin, as if the black hole resonates through the disk, sending ripples of brightness outward, subtle hints that the spacetime near the horizon has its own natural frequencies. Another powerful tool is the study of Doppler shifts, the change in wavelength of light from gas moving at high speeds. Gas on the side of the disk rotating toward us emits bluer light, gas on the side rotating away emits redder light, and by measuring this asymmetry, astronomers reconstruct the speed and orientation of the disk and infer the mass of the black hole with remarkable precision. These Doppler signatures also reveal the rotation of the black hole itself. For the spin influences the inner edge of the disk, shifting the location of stable orbits, changing the pattern of emission, modifying the asymmetry and brightness, all of which can be measured and interpreted. When the black hole spins rapidly, the disk can extend closer to the horizon, reaching deeper into the gravitational well, releasing more energy, producing higher temperatures and shifting the spectrum of emitted light. This change is visible from vast distances. A fingerprint of rotation encoded in the glow of the disk, in the shape of the spectrum, in the timing of the oscillations, in the tilt of the iron emission lines, in the structure of the corona. All of these observations form layers of evidence, each one reinforcing the same conclusion, that the object at the center is compact, massive, dark, and consistent with the predictions of a black hole. But the observations do more than confirm existence. They reveal behavior. The way the black hole interacts with its environment, the way it grows over time, the way it releases energy, the way it influences the galaxy around it. Even gravitational waves contribute to this picture. Ripples in spacetime produced when two black holes spiral together, waves that carry information about the mass and spin of the merging bodies, waves that confirm the predictions of relativity with extraordinary precision, waves that reveal black holes not only as objects of extreme gravity, but as participants in cosmic evolution, colliding and merging across the history of the universe. These waves travel undisturbed across billions of light years, their shapes preserved, their frequencies unchanged, their patterns reflecting the final orbits of the merging black holes. And when they reach Earth, they shift the positions of detectors by amounts smaller than the width of a proton. Yet these shifts are detectable, measurable, and unmistakable. Through these waves, astronomers observe black holes not as silent objects, but as dynamic participants, sources of energy and motion, objects that reshape spacetime through their collisions, objects that grow through mergers, objects that influence the evolution of galaxies and clusters. Observing the unseen is not a single technique, but an ensemble of methods, each revealing part of the story, each contributing a thread to the tapestry, each confirming the same truth, that the universe contains regions where spacetime curves so deeply, so smoothly, so predictably, that all paths lead inward, all light bends, all motion echoes the quiet signature of the black hole. And as these ideas settle, you move gently into the next part of the story, how black holes grow, how they merge, how their influence stretches across cosmic time, a continuation of the same calm, analytical drift, moving from observation to evolution. The most delicate part of observing a supermassive black hole lies in the transformation between raw signals and meaningful understanding, the long chain of interpretation that turns faint energy into a picture of something that cannot be seen directly. When an astronomer looks at the sky through a radio dish, they are not seeing an image in the familiar sense. They are detecting slight variations in the phase and amplitude of waves, variations that must be combined, filtered, aligned, and processed through algorithms that have been refined over decades. The Event Horizon Telescope does not capture photographs, it captures timing, differences measured with exquisite precision, microseconds separating the arrival of waves at one telescope from another, a pattern of correlations that encodes the shape of the source, like a shadow woven from timing alone. This is why the final images appear soft, blurred, almost dreamlike. They are reconstructions of something deeply mathematical, a translation of the structure of spacetime into a picture comprehensible to human eyes. The softness of these images is not a flaw. It is a reflection of the physical limits of resolution, the scale of the object, and the distance across which its signals must travel. To see structure near the event horizon, light must pass through gas, dust, magnetic fields, and turbulent plasma, all of which distort the signal slightly, adding noise, shifting the pattern, introducing uncertainties. These uncertainties do not erase the information. They simply remind us that nature is not always clearly outlined, that reality often arrives wrapped in complexity, requiring patience, reconstruction, and interpretation. When the first image of a supermassive black hole was produced, the dark circular region surrounded by a glowing ring, it was not merely a scientific milestone, it was a demonstration of the power of inference, the ability to extract structure from faint signals and to turn the invisible into the visible through careful analysis. The ring itself is not the event horizon. It is a region where light orbits the black hole, a boundary of unstable trajectories, a region where photons can circle many times before escaping, their paths bending under the influence of immense curvature. This ring forms the bright outline in the images, a glowing loop shaped by radiation from hot plasma swirling near the black hole, radiation that bends, twists, and arcs around the central void, revealing the geometry of spacetime itself. Even this radiation is not emitted uniformly. The brightness varies because the plasma moves at tremendous speeds, its motion causing relativistic beaming, an effect where radiation becomes brighter in the direction of motion and fainter in the opposite direction. This asymmetry is part of the signature, a clue to the rotation of the black hole, a hint that the surrounding matter is swirling with directional preference, falling inward along paths shaped by the twist of spacetime. Rotation can be inferred not through a direct image, but through how the brightness shifts around the ring, how the shadows distort, how the patterns evolve with time, a subtle fingerprint embedded in the flow of light. One of the most challenging aspects of observing black holes is the extreme faintness of some of these signals, particularly when the black hole is dormant, not feeding, not producing bright jets or strong X-rays, just resting in quiet equilibrium. In such cases, astronomers rely on indirect methods, tracing the motions of stars, measuring Doppler shifts, watching the curvature of orbits, looking for deviations from Newtonian estimates, all of which hint at a compact, massive object. In the center of our own galaxy, this is exactly how the presence of the supermassive black hole was confirmed by watching stars move, tracking their positions over many years, mapping their paths as they curved tightly around an invisible point. One particular star, with a fast, highly elliptical orbit, became a centerpiece of this detection, its motion revealing the mass of the central object, its acceleration implying a deep gravitational well, and its return to the same point, proving the presence of a single dominant mass. This method remains one of the most elegant ways to observe the unseen. No need for radiation. No need for an accretion disk, only the gravity itself serving as a signal, a pure expression of mass shaping space. Another method involves studying gas clouds drifting near the nucleus, their temperatures, their velocities, and the way they brighten when compressed by the surrounding environment, all serving as tracers of the gravitational potential. The closer these clouds approach the center, the more their motion reveals, the more their light carries information, the more their patterns reflect the presence of a compact, massive object. Sometimes astronomers observe flares, brief increases in brightness caused by turbulence near the event horizon, or by magnetic reconnection events, or by small parcels of gas plunging inward, heating rapidly and emitting radiation before crossing the boundary of no return. These flares offer tiny glimpses of activity near the edge, snapshots of physical processes unfolding in extreme conditions, moments that help refine models, confirm predictions, and anchor theories in observation. Even gravitational waves, ripples in spacetime itself, serve as a way of observing the unseen. When two black holes merge, their mass and motion generate waves that travel across the universe, carrying the imprint of the final orbit, the collision, and the settled state of the remnant. These waves reveal mass, spin, and the nature of the final object, allowing astronomers to observe a process that emits no light, a process that unfolds entirely in the fabric of spacetime. This ability to detect the merger of black holes has transformed how we study them, providing an entirely new window into their population, their distribution, their evolution, and their role in shaping galaxies. But even with all these tools, there is always uncertainty, a margin of interpretation, a region where models must fill in gaps, where simulations guide understanding, and where observations remain incomplete. This uncertainty is not a flaw of astronomy. It is part of the beauty of studying objects hidden behind horizons, objects that cannot be seen directly, objects that reveal themselves through influence, through motion, through radiation, through waves, through echoes in the geometry of space. The softness of the images, the faintness of the signals, the need for long integration times, all contribute to a sense of quiet, a sense that the cosmos does not shout its secrets, but releases them slowly, carefully, across decades of observation. This slow revelation mirrors the nature of supermassive black holes themselves, objects that evolve over immense timescales, whose processes unfold gradually, whose presence is steady, enduring, and patient. Even when the black hole is active, even when jets stretch across thousands of light years, even when the nucleus brightens with accretion, the human experience of observing these events remains gentle, mediated by instruments, filtered through analysis, arriving to us as soft lines on graphs, or faint patterns in radio maps, or subtle oscillations in wave signals. The calmness of observation contrasts with the raw energy near the event horizon, but this contrast enhances the meditative nature of the study. A reminder that understanding can emerge from quiet examination, from slow accumulation, from long contemplation. When astronomers interpret the signals from the Event Horizon Telescope, they build models that simulate how plasma behaves near the black hole, how magnetic fields twist and organize, how light bends and escapes, how shadows form, and how the structure evolves. These models are compared with the data, refined repeatedly, until the reconstruction converges on a shape that reflects both theory and observation, a shape that captures the essence of the environment near the horizon. The result is an image that is not a simple snapshot, but a synthesis, a collaboration between physics and measurement, a depiction of space-time shaped by mass and revealed through waves. In this sense, observing a supermassive black hole is an act of interpretation, a process that requires trust in physical laws, trust in mathematics, and trust in the stability of the universe itself. The black hole does not change during the observation. Its mass remains consistent, its gravity constant, its environment shaped slowly over time. This stability allows astronomers to gather signals from around the world, to combine them coherently, to extract a structure from the faintest flicker of radiation, and to reveal the quiet imprint of the event horizon. And in that imprint, in that soft glow surrounding a region of darkness, there is a profound stillness, a calm that matches the tone of this exploration, a reminder that the cosmos is vast, deep, and patient. This completes Section 5, and the mind drifts naturally toward the next subject, the ways in which these giants grow, merge, and evolve across the slow, unhurried stretch of cosmic time, a transition into the next section, quietly, smoothly, like a galaxy settling into its own rotation. Growth, for a supermassive black hole, is not a sudden event, nor a single process, but a long and gradual shaping of spacetime itself, a slow accumulation of mass that unfolds across billions of years, guided by gravity, regulated by the environment, and expressed through the deep, quiet structure of the cosmos. To imagine how these giants grow, you can picture the center of a galaxy as a region where matter flows differently than it does elsewhere, where gas does not drift freely, but spirals inward under the pull of gravity, where stars pass near the nucleus, sometimes losing energy and gradually shifting closer across many orbits, where dust, molecular clouds, and fragments of stellar remnants all contribute to the slow feeding of the central mass. In such an environment, the supermassive black hole acts as an anchor, not actively pulling matter like a vacuum, but shaping the gravitational landscape so strongly that matter naturally sinks toward it, like water finding the deepest point of a basin, a gentle, steady descent, regulated by the geometry of space-time. Most of the material entering this environment does not fall inward all at once. It forms a disk, a flattened structure defined by angular momentum, a region where gas rubs against gas, slowing through friction, releasing energy, glowing softly in X-rays and infrared light, and slowly losing the rotational support that keeps it aloft. This disk is the main gateway through which matter joins the black hole, a slow conveyor of mass, transforming the gravitational energy of infalling gas into radiation and letting the leftover material drift inward toward the event horizon, crossing it silently, without trace, without signal, becoming part of the growing central mass. This process can be astonishingly bright when the disk is full, producing quasars, objects so luminous that they can outshine entire galaxies, radiating energy as gas heats to extreme temperatures before falling inward. But the brightness is temporary, a phase, a moment in the long life of the black hole, because accretion is limited by the supply of available gas, and galaxies do not maintain constant inflows over time. Instead, the feeding of a supermassive black hole tends to occur in episodes, times when gas flows inward through gravitational disturbances, mergers, collisions of molecular clouds, or the settling of cold gas toward the nucleus, each episode adding growth, each episode shaping the long-term evolution of the black hole. Between these episodes, the black hole can become quiet, nearly invisible, with little radiation, little accretion, just the silent curvature of spacetime at the center of the galaxy, waiting for the next event. The next flow of material, the next transformation. Another pathway for growth emerges from the life cycles of stars. Near the galactic center, stars can approach close enough to be disrupted, torn apart by tidal forces, their material spiraling inward as a brief and intense flare, adding mass in a sudden but localized event. These tidal disruptions do not happen frequently, but over millions of years they contribute, providing moments of rapid feeding embedded within the long quiet stretches. Yet even this pathway is small compared to the impact of galaxy mergers, cosmic collisions that reshape entire structures, bringing together two massive galaxies, each with its own central black hole, each carrying a history of stars, gas, and dark matter. When galaxies merge, their stars pass through each other, their gas clouds collide and compress, triggering bursts of star formation and driving gas inward toward the centers, fueling active nuclei and feeding the central black holes. During these mergers, the central black holes draw closer to each other, spiraling inward through the dense environment, losing energy to the surrounding stars, and eventually becoming gravitationally bound, forming a binary system that continues to contract over time. This contraction can continue for millions of years, with the orbit shrinking as gravitational interactions carry energy away, until the black holes are so close that gravitational waves dominate the energy loss, sending ripples through the curvature of space, slow, steady, and powerful. Eventually, the two black holes merge, forming a single, larger supermassive black hole. Its mass equal to the sum of the two initial masses minus a small fraction radiated away as gravitational waves, and its spin determined by the angular momentum of the merging system. This process contributes significantly to growth, especially in large galaxies, where multiple mergers throughout cosmic history have assembled the enormous masses we observe today, some exceeding billions of solar masses. Silent giants built from the slow combination of smaller structures. The gravitational waves from these mergers are too low in frequency for ground-based detectors, their oscillations unfolding across months or years, like an extremely slow vibration moving through the fabric of the universe. But pulsar timing arrays, networks of rapidly spinning neutron stars, detect these subtle undulations, tiny shifts in the arrival times of pulses across the sky, revealing the presence of merging supermassive black hole binaries scattered throughout the cosmos. This detection shows that the universe is filled with the slow, rhythmic hum of gravitational waves, a background murmur created by countless mergers across cosmic time, each one contributing to the growth of the central objects we now study. Even this cosmic hum evolves, changing with the rate of galaxy mergers, shaped by the large-scale structure of the universe, and revealing the deep connection between galaxy evolution and black hole growth. Another layer of growth emerges when considering the early universe, a time when the first massive black holes formed far earlier than expected, masses reaching hundreds of millions of suns in less than 1 billion years, a mystery that continues to challenge astrophysics. These early black holes likely began as massive seeds, far larger than the remnants of typical stars, perhaps formed from direct collapse, where primordial gas clouds, devoid of heavy elements, cooled inefficiently, collapsing into massive structures without fragmenting into stars. These seeds could reach tens of thousands of solar masses, large enough to grow rapidly through accretion, reaching supermassive size before the universe had expanded significantly. Alternatively, the first stars may have been far larger than the stars we see today, collapsing into black holes with substantial mass, providing another pathway for early growth. These scenarios remain areas of active research, with simulations exploring how gas cooled, how radiation influenced collapse, and how dark matter halos shape the formation of early black hole seeds. The uncertainty surrounding these seeds is not a flaw, but a reminder of the depth of the unknown, a sign that even the most massive structures in the universe still carry mysteries, threads of inquiry that pull scientists deeper into the fabric of cosmic history. As time progressed, mergers became more frequent, gas inflows more complex, and galaxies assembled into larger structures, feeding their central black holes through repeated episodes of accretion and collision. This interplay between galaxies and their central black holes evolved into a feedback system, a loop where the activity of the black hole influences the galaxy and the structure of the galaxy influences the feeding of the black hole. When the black hole accretes too rapidly, it can emit winds, jets, or radiation that heats surrounding gas, preventing it from cooling and reducing the rate at which new stars form. This feedback can stabilize the galaxy, regulating the balance between star formation and gas inflow, maintaining a long-term equilibrium, and shaping the structure of the galaxy over billions of years. In quieter phases, the galaxy provides gas more gently, allowing the black hole to grow slowly, shifting its mass through persistent but mild accretion, creating the calm, stable systems observed in many mature galaxies today. Through all these pathways, the growth of a supermassive black hole becomes a record of the galaxy's past, its mergers, its inflows, its episodes of star formation, its disturbances, its interactions with the cosmic web. The black hole is both a product of its environment and a shaper of it, a central figure in the quiet architecture of galaxies, a structure whose growth is inseparable from the evolution of cosmic history. And as these threads intertwine, the narrative drifts toward the next frontier, the conceptual edge where physics meets philosophy, where the nature of horizons, information, and quantum structure invites deeper contemplation, carrying the mind gently into the mysteries of knowledge itself. The growth of a supermassive black hole is shaped not only by what falls in, but also by what fails to fall in, by the delicate balance between inflow and outflow, between gravity pulling inward and energy pushing outward, a balance that determines how fast a black hole can grow and how its presence influences the galaxy around it. Every black hole has a natural limit to its growth rate, set by the amount of energy released as matter spirals inward. Energy that radiates outward, pushing back against the inflowing gas, heating it, accelerating it, and sometimes driving it away from the nucleus altogether. This limit is known as the Eddington rate, a balance point where the outward radiation force equals the inward pull of gravity, a quiet threshold built into the physics of accretion, a natural ceiling on how quickly mass can be added. When a black hole accretes near this threshold, it shines brightly, becoming an active galactic nucleus, or a quasar, illuminating the distant universe with radiation generated near the event horizon, radiation that emerges from the deep gravitational well, carrying information about temperature, density, and magnetic fields. Even at this level of brightness, the growth is slow by human standards, requiring millions of years for significant mass changes, because the mass of a supermassive black hole is already enormous. And each addition shifts it only slightly, like adding drops to a vast ocean. This slowness is part of their character, steady, patient, unchanged by brief fluctuations, responding only to long-term patterns, long-term flows, and long-term cosmic behavior. There are moments, however, when growth becomes more rapid, when the black hole operates near its maximum sustainable accretion rate, consuming gas efficiently, transforming infalling material into radiation, and letting the remainder drift through the horizon. But these phases rarely last, because the very radiation that signals rapid growth tends to heat the surrounding environment, reducing the availability of cool gas, suppressing inflow, and eventually ending the active phase. This self-regulating cycle is part of the feedback loop that shapes galaxy evolution, a gentle push and pull between growth and suppression, between feeding and quieting, between bright periods and dormant intervals. Feedback can take many forms, sometimes appearing as winds, broad outflows of gas accelerated by radiation pressure, moving through the central region, disrupting molecular clouds, and changing the conditions under which stars can form. Sometimes feedback takes the form of jets, narrow, focused beams shaped by magnetic fields, launched from the region near the event horizon, stretching far beyond the galaxy, interacting with intergalactic gas, heating it, compressing it, and sometimes preventing it from cooling. These jets are among the most powerful structures in the universe, capable of extending tens of thousands of light years, shocking the gas they encounter, and influencing entire galaxy clusters. Yet their effect on the local growth of the black hole is subtle, because jets remove angular momentum from the disk, allowing matter to fall inward more easily, even as they expel a small fraction of the surrounding gas. The relationship between jets and growth is therefore complex, with some phases boosting accretion efficiency and others slowing it, depending on the configuration of magnetic fields, the availability of gas, and the thickness of the accretion disk. Over cosmic time, this dance of inflow and outflow shapes the final mass of the black hole, creating the distribution of sizes observed today, from millions to billions of solar masses. Each one the product of billions of years of combined processes. Another factor that influences growth is the alignment of angular momentum, the direction of rotation of gas falling inward, because a black hole with a strong spin can limit how close stable orbits can approach, shifting the location of the innermost stable circular orbit, changing how energy is radiated, and altering the efficiency of accretion. A rapidly rotating black hole allows matter to fall into a deeper gravitational well, releasing more energy per unit of mass, and therefore requiring less mass to produce a given luminosity, making the feeding process more efficient and potentially limiting the total amount of material that can be added before feedback intervenes. Conversely, a slowly rotating or non-rotating black hole is less efficient, radiating less energy, allowing higher mass inflow rates, and potentially growing faster, though this growth may be interrupted by mergers that can reset or invert spin direction. The net result is that spin influences growth, and growth influences spin, creating a long-term evolutionary trajectory that reflects the entire history of accretion and mergers. This relationship also affects the shape of the event horizon, the dragging of spacetime near the boundary, and the behavior of light near the photon orbit, all of which leave subtle signatures observable through high-resolution imaging and timing methods. The seeds of supermassive black holes add yet another dimension to their growth story, because the initial mass sets the pace at which they can reach their modern sizes, affecting how quickly they become active, how luminous they can be, and how early they influence their host galaxies. If seeds are massive, growth can begin earlier, leading to quasars that shine brightly in the early universe, observed today as faint signals traveling across billions of years of cosmic expansion. If seeds are small, growth requires more time, slowing their emergence, reducing the number of bright quasars in early epochs, and altering the predicted distribution of black hole masses. Observations of early quasars suggest that some seeds must have been massive, given the limited time available for growth, reinforcing the idea that direct collapse, or early massive stars, played a significant role in creating the first central black holes. As time continued, the role of galaxy mergers became dominant, especially in forming the largest supermassive black holes, those with masses exceeding a few billion suns, because mergers not only bring together black holes, but also drive gas inward, creating bursts of accretion that accelerate growth. This process continues even now, though at a slower pace, with fewer galaxy mergers occurring today, and with galaxies more widely separated due to cosmic expansion. The slow drift of cosmic time becomes deeply apparent in this context, because the processes that shape supermassive black holes do not operate on human timescales, nor even on the timescales of stars, but on intervals closer to the age of the universe itself. A deep, quiet evolution unfolding across billions of years. The central black hole of a galaxy is therefore not a static feature, but a living record, carrying the memory of collisions, the imprint of ancient gas flows, the echoes of gravitational waves, and the signature of early seed formation. Its mass, its spin, its environment, all reflect the combined influence of cosmic history, a tapestry woven from many processes, each operating at its own pace, yet all contributing to the giant we observe today. And as you drift through these thoughts, the story gently transitions toward deeper philosophical terrain, toward questions not only about growth, but about knowledge, about horizons, and about the nature of information in a universe shaped by gravity and quantum mechanics. The next section explores these ideas, the ones that rest at the boundary of understanding, where the behavior of black holes challenges the foundations of physics and invites contemplation of mysteries that remain unresolved, quietly, softly, drifting into the unknown. The deeper you drift into the study of supermassive black holes, the more you begin to feel the quiet boundary between what is known and what remains somewhere just beyond reach. A horizon not of matter, but of understanding. A place where equations begin to stretch, and where intuition begins to soften. Supermassive black holes sit at this boundary naturally, because they combine gravity at its strongest with quantum behavior at its most mysterious, bringing together two frameworks of physics that work beautifully on their own, yet resist merging into a single seamless description. In the regions far from the event horizon, gravity behaves predictably, curving spacetime smoothly, guiding the paths of stars, and bending the trajectories of photons. A realm where general relativity gives precise answers, clear predictions, and stable solutions. But as you move inward, toward the horizon, and then toward the singularity itself, the equations begin to lose their clarity, not because the math is wrong, but because the conditions become so extreme that the rules we currently rely on were never designed to operate there. The singularity is the clearest example of this tension, a theoretical point where density becomes infinite, where curvature blows up, and where our equations no longer describe physical reality, but only the limit of their applicability. Most physicists believe the singularity is not a literal point, not an actual place of infinite density, but rather a signal, a signpost, pointing toward the breakdown of classical theory, a reminder that quantum gravity must eventually step in to replace the divergence with something physically meaningful. Yet no one knows what that something is, because quantum gravity remains unfinished, a patchwork of ideas from string theory to loop quantum gravity, to emergent spacetime models, each providing hints, each offering partial explanations, yet none forming a complete solution. This uncertainty creates a kind of philosophical horizon, parallel to the physical one, a boundary where we must accept that our present knowledge is incomplete, and where the unanswered questions remain suspended, quiet, waiting. One of the deepest puzzles arises from the behavior of information, because in classical general relativity, anything that crosses the event horizon is lost forever, its details, its structure, its quantum state, all erased from the observable universe. But in quantum mechanics, information cannot be destroyed, a fundamental rule built into the mathematics of wave functions, probabilities, and the conservation of quantum states. These two principles, loss and preservation, clash directly at the event horizon, producing the famous black hole information problem. A conflict not caused by observational limits, but by theory itself, a contradiction that demands resolution, and yet remains unsolved. The tension is subtle, and yet profound. If information is lost, quantum mechanics breaks, and unitarity fails, undermining the entire framework of microscopic physics. If information is preserved, general relativity's description of horizons and singularities must be incomplete, requiring new physics, new mechanisms, or new structures embedded in space-time. Some proposals suggest that information is encoded on the horizon itself, stored in a thin holographic layer, a surface where quantum degrees of freedom reside, translating the volume of space inside into a two-dimensional representation, not unlike how a hologram encodes a three-dimensional scene on a flat sheet. This idea, the holographic principle, emerges from deep mathematical results in quantum gravity, suggesting that spacetime may not be fundamental, but emergent, arising from more primitive quantum information woven into a geometric form. Under this view, a black hole is not an object with a missing center, but a highly complex quantum system, where information is stored in correlations, entanglement patterns, and horizon microstates, hidden from ordinary observation, yet preserved in the underlying structure. Another approach proposes that information escapes slowly through Hawking radiation, but encoded in a highly scrambled pattern, a pattern indistinguishable from thermal noise unless viewed holistically, a process requiring enormous timescales, far beyond the age of the universe, yet still consistent with the conservation of quantum information. In this picture, the black hole becomes a quantum processor, taking in data, scrambling it, and releasing it again in subtle, nearly invisible fragments, a quiet evaporation process that preserves every detail. Even if no observer could practically extract it, there are also proposals involving remnants, hypothetical objects left behind after evaporation ends, tiny storerooms of information, holding everything that fell into the black hole, preserving unitarity at the cost of introducing unexplained stable particles. Each possibility points toward a different view of spacetime, of quantum mechanics, of the deep structure of the universe, and each remains unproven. Leaving the horizon of understanding wide open, soft, porous, and still waiting for clearer insights. What makes this frontier so fascinating and so calming to contemplate is that the science here is not frenetic, not rushed, but patient, spanning decades of theoretical work, layer upon layer of refinement, and a slow convergence toward deeper principles. As you drift through these ideas, you begin to sense how the study of black holes reshapes our philosophical intuition, pulling our thoughts toward the fundamental nature of reality, toward questions about what space and time truly are, toward the possibility that the universe is built from information, from correlations, from structures more abstract than matter itself. This perspective softens the boundary between physics and metaphysics, not by abandoning science, but by letting science lead naturally into the unknown, toward the edge where new theories must arise, and where present knowledge remains incomplete. Supermassive black holes play a central role in this philosophical shift, because they are both physical objects, anchoring galaxies, shaping cosmic structure, influencing star formation, and simultaneously conceptual gateways, challenging our deepest assumptions, and highlighting the limitations of current theory. Their horizons are not merely surfaces in spacetime, but symbols, illustrations of the limits of observation, and reminders of how much remains unseen, unmeasured, and perhaps unmeasurable. Thinking about them invites a kind of quiet humility, a recognition that the universe is allowed to be larger than our theories, richer than our models, and more intricate than our current mathematics can express. This humility is not discouraging, but peaceful, a reminder that knowledge grows slowly, and that curiosity itself is part of the journey, a gentle force guiding us toward deeper clarity, even if the full answers remain far away. Hidden behind horizons of their own, these ideas drift through the mind, settling softly, calmly, like dust in a sunbeam, encouraging reflection, not urgency, connecting the outer cosmos with quiet inner thought, where wonder becomes a companion to rest. And as this part of the journey comes to a close, the narrative continues inward, toward the deeper aspects of the information problem, toward the possibility of quantum gravity, toward the horizon where knowledge bends and reshapes, leading naturally into the next part of this section, where the themes unfold even more deeply and the philosophical landscape widens. As the horizon of understanding widens, you notice how every question about supermassive black holes slowly transforms into a question about reality itself, about the structure beneath spacetime, about the rules that govern information, and about what it truly means for something to exist, to persist, to be measurable, or to slip beyond measurement entirely. The information problem continues to unfold at this deeper level, not as a simple puzzle about particles, but as a tension between two worldviews, one rooted in smooth geometry and the other woven from quantum discreteness, probability, and entanglement. In general relativity, the horizon is a clean surface, a silent boundary, a mathematical edge where escape becomes impossible, a location where trajectories bend inward, never outward, a place that divides the universe into two regions, one visible, one forever hidden. But in quantum mechanics, boundaries are never truly sharp. Wave functions overlap, probabilities seep across surfaces, and nothing is ever perfectly confined. Not even light, not even space-time itself. This mismatch produces a quiet tension, an unease that grows the closer you look, as if the horizon were a veil made of two incompatible materials, one continuous, one granular, both trying to describe the same subtle surface. Some researchers imagine the horizon as a thermodynamic object, with temperature, entropy, and microscopic states. A surface that behaves as if it were composed of countless degrees of freedom, each holding a sliver of information, a record of whatever has interacted with the black hole. This idea emerges from the formula for black hole entropy, a remarkably simple expression, showing that the entropy scales not with the volume inside, but with the area of the horizon, a clue that the surface is fundamental, not the interior. It suggests that space-time might store its information holographically, as if the depth of a region is encoded on its boundary, much like how a three-dimensional scene appears when encoded on a thin sheet of holographic film. Contemplating this principle feels like drifting toward a deeper layer of physics, where geometry and information merge, and where the universe becomes less like a physical place and more like a vast, structured computation. A quiet network of correlations, patterns, and emergent spacetime. In this view, the black hole no longer feels like an object swallowing information, but rather a system rearranging it, scrambling it, and distributing it over the horizon in ways that are mathematically reversible, even if practically impossible to decode. But this interpretation leads to new puzzles, because if the horizon stores information, then what happens when the black hole evaporates? Very slowly, releasing Hawking radiation, photon by photon, until nothing remains except the radiation itself. The radiation seems thermal, featureless, suggesting that information has been destroyed, yet quantum theory forbids such destruction. This contradiction leads to the possibility that the radiation is not truly random, but subtly correlated, structured in hidden ways, encoding the past in patterns too faint to detect, like whispers embedded in static, meaningful only when viewed as a whole. As you drift through these ideas, you begin to see how black holes serve as tests, as laboratories for theoretical physics, revealing the boundaries where current frameworks fail, and pointing toward the need for something more fundamental. Some physicists imagine spacetime itself dissolving into quantum threads, loops of geometry, or vibrating strings, tiny mathematical objects whose collective behavior gives rise to the smooth curves of gravity, and whose excitations replace the singularity with something finite, consistent, and describable. Others suspect that spacetime is emergent, not fundamental, arising from entanglement patterns, the same way temperature arises from the motion of particles, or the way fluid behavior arises from countless molecular interactions. If this is true, then the horizon is not simply a place where geometry changes, but a boundary in the structure of quantum information. A transition between regions of entanglement, shaped by deeper principles. In this picture, the black hole becomes something like a phase of matter, a state defined by the way information is organized, not merely by mass or curvature, a new phase of spacetime with its own rules and its own microscopic structure. These ideas are still theoretical, soft, incomplete, like sketches waiting to be filled in. Yet they offer glimpses of what a future theory of quantum gravity might look like, a theory capable of describing both the cosmic scale and the quantum scale without contradiction. As the thoughts settle, another puzzle emerges quietly, a question that stretches beyond information and into ontology, into the nature of existence itself. Inside the event horizon, the future is curved inward. Every possible path points toward the singularity, and the geometric structure forces all matter to move deeper, never outward. But what does it mean to say that something exists inside such a region, when no information about its state can ever reach the outside world, when no observer can interact with it, measure it, or verify its continued presence? Some philosophers argue that existence requires observability, that a world completely cut off from causality becomes physically meaningless, a mathematical construction. Not a real region. Others argue that reality is not dependent on observation, that the interior exists regardless of who or what may witness it, just as distant galaxies existed long before any light from them reached Earth. Yet both viewpoints highlight a deeper issue, that black holes force us to distinguish between mathematical description and physical meaning, between what can be known and what remains inherently hidden. This tension is not uncomfortable, but strangely calming, a reminder that the universe contains mysteries that remain intact even under the brightest reasoning, mysteries that preserve a sense of depth, a sense of quiet wonder. Supermassive black holes become philosophical mirrors, reflecting our assumptions back toward us, revealing where they hold and where they unravel. They force us to confront the idea that spacetime may not be the backdrop of reality, but an emergent feature, arising from something more abstract, something deeper, something still unarticulated. As these reflections drift through the mind, the horizon becomes more than a surface, more than a boundary, more than a point of no return. It becomes a symbol, a reminder of the quiet frontier that every field of science eventually reaches, where questions continue, where curiosity guides, and where certainty fades into stillness. Even the singularity takes on a different feel, no longer a catastrophic endpoint, but a placeholder for future understanding, a sign that our theories remain incomplete, and that deeper principles lie waiting, just out of reach, beyond the horizon of current knowledge. These thoughts settle like dust upon calm water, spreading slowly, forming ripples that merge into stillness, a reminder that not every mystery demands resolution tonight, that resting with the unknown is part of the journey and part of the beauty of studying the universe. And as this section draws to its quiet close, the narrative drifts gently toward the final portion of the journey, the soft epilogue, where the supermassive black hole returns once more to its role as the silent center, the steady anchor of a galaxy, and a metaphor for the calm that emerges when curiosity, understanding, and rest finally settle into one another. Everything you have drifted through returns now, quietly, slowly, like the soft orbit of a star completing a long, gentle loop around its galactic center. The idea of a supermassive black hole, once sharp, once distant, now feels calmer, broader, a presence rather than an object, a quiet mass deep beneath the structure of everything, shaping without announcing itself, guiding without motion, influencing without sound. If you picture a galaxy now, any galaxy, spiral or elliptical, grand design or irregular, there is a steady center you can feel, something weightless in appearance, yet heavier than anything else the universe has learned to construct, a silent gravitational heart. And around it, the stars drift in their orbits like slow rivers of light, each one following the curvature drawn by the mass beneath it, not forced, not pulled violently, but guided along a path that has existed for millions of years, paths so stable, so predictable, that they become almost like the memory of the galaxy itself. When you imagine this, you begin to sense the profound stillness at the center, the calm core where spacetime bends into its deepest well, not chaotic, not stormy, but quiet, smooth, like the surface of a lake that stretches farther than sight, where gravity sinks deeply, yet without turbulence. Supermassive black holes do not disturb their surroundings through violence. They organize them. They are engines of structure rather than destruction, massive enough to hold a galaxy's architecture together, yet distant enough from most stars to let entire civilizations rise and vanish, never feeling their influence as anything more than background gravity. In this way, they become symbols of the universe's patient design, objects formed across unimaginable stretches of time, grown from smaller seeds, fed by gas, by stars, by mergers, by gentle accumulation, until they reach millions, even billions of solar masses, yet remain hidden, dark, invisible, except through what circles them. Their silence becomes part of their nature, a reminder that not everything powerful must announce itself, and not everything vast must be loud. Sometimes the greatest forces are the quietest ones, the ones that shape the world simply by being there, steady, constant, unchanging across the lifespan of galaxies. If you drift outward now, further from the galactic center, letting the stars grow sparse, letting the darkness widen between them, you can sense the black hole fading behind you, not disappearing, but settling back into its role, a distant anchor, a constant reference point, a mass deep below the visible world. And as you move through this mental space, through this imagined galaxy, you begin to realize that even the emptiness is shaped by the gravity at the core. That even the stars tens of thousands of light years away carry the memory of that central mass. Their orbits curved subtly, their motions guided gently, their paths connected through a fabric held together by the weight at the center. This knowledge does not need to be solved tonight. It only needs to be felt. The way a sleeping traveler feels the hum of an aircraft, not analyzing the engines, only sensing the steady support beneath them, letting the constant vibration soothe them into rest. You can let the enormity of the universe shrink now, gently, softly, until it becomes a distant backdrop again, not overwhelming, not impossible, just present, patient, vast beyond measure, yet strangely calming. The supermassive black hole at the center of your imagined galaxy becomes a point again, a quiet dot of influence, a symbol of how the universe balances forces, how it arranges its matter, how it creates order from collapse and stability from inward fall. If you observe it from this distance, you may sense how its gravity creates rhythm, a cosmic heartbeat, slow, steady, a pulse that travels outward for tens of thousands of light years, felt only through the long arcs of stellar orbits, but felt nonetheless. The galaxy becomes a great wheel, turning gently, its arms drifting through interstellar space, its dust glowing softly in infrared, its stars pulsing faintly with their own internal thermonuclear breath. And at the very center, hidden behind layers of dust and stars and gas, the black hole remains, the silent axis, the still point around which everything rotates. There is a comfort in that image, a reminder that even in systems of unimaginable scale, there is a center, there is a structure, there is a quiet gravitational foundation that holds everything together. Just as in the smaller structures of life, thoughts turn around something central, experiences orbit memories. Emotions circle around quiet cores too deep to name, and consciousness drifts like a star, pulled gently by internal gravities. The universe offers these metaphors not because they are poetic, but because they are natural, because physics itself contains forms of calm that mirror the patterns of thought, and because supermassive black holes, despite their power, embody a special kind of tranquility. Even the extremes of spacetime, even the boundaries where light cannot escape, follow rules, remain predictable, stay faithful to the mathematics that describes them, a reassurance that the universe is intelligible, coherent, structured even in its most alien places. And so the journey ends not in collapse, not in mystery alone, but in a kind of quiet alignment, an understanding that the universe is both immense and serene, dynamic and stable, filled with unknowns, yet guided by deep principles that flow through every scale. The galaxy around you turns slowly, arms stretching through millions of stars, dust glowing in soft bands, halo particles drifting in orbits longer than the history of humanity, everything moving, yet everything calm. And deep inside, far beyond where any light can emerge, the supermassive black hole rests, not asleep, not awake, but simply existing, a region of curved spacetime, a quiet center. A reminder of the strange and beautiful shapes gravity can create. Let that image settle now, a whole galaxy turning in silence, a center that will endure for billions of years, a gravitational well so deep yet so peaceful from far away that it becomes a symbol of cosmic rest. You can let the thought drift, becoming lighter, becoming softer, letting the weight of the universe fall away, leaving only the calm, the rhythm, the slow turning of stars. Curiosity and rest do not oppose each other here. They complement each other. Because the more you understand the stability of these cosmic structures, the easier it becomes to feel steady yourself, to feel supported, to feel the quiet presence of something vast beneath the surface of things. You may imagine the galaxy dimming now, its stars fading to small points, the spiral arms dissolving into haze, the black hole shrinking into a faint suggestion. A distant center you no longer need to visualize, just a feeling of gravity, deep, soft, receding, and as it fades, the stillness remains, a calm that persists even after the imagery dissolves, a spaciousness that does not depend on stars or horizons, a quiet place within the mind that mirrors the quiet heart of the galaxy. The universe continues turning, the galaxies continue drifting, the black holes continue resting in their silent centers, and you can rest with them. Letting the calm of cosmic time settle over you, letting the vastness become something soothing, letting the quiet gravity of understanding bring you gently inward. Here, in this final moment, the cosmos becomes soft, the darkness becomes warm, and the supermassive black hole becomes nothing more than a peaceful reminder that even in the deepest mysteries there is tranquility, order, and space for rest. Let yourself drift now, slowly, quietly, as the galaxy turns. And the universe stretches out around you, endless, calm, and welcoming, a place where thought loosens and the mind settles into its own quiet orbit. The journey ends here in silence, in stillness, in the soft gravity of sleep.